Okay, thank you everyone for coming. Hi, I am Lynn Clark, and I make code cartoons. And I also work at Mozilla on things like WebAssembly, which is what I'm going to be talking about today. And I'm joined by Till Schneidereit, who leads our WebAssembly tooling efforts at Mozilla. And so he'll be filling us in on some of their work. So first off, what is WebAssembly? WebAssembly is a way of running programming languages other than JavaScript on the web. So up until now, to run code on a web page, the only language that you could use was JavaScript. But now there's WebAssembly. So if you want to do a computation, do some kind of change in response to an event, you can use other languages to do that, like C or C++ or Rust. Now, I wish I had time to go into more detail about the basics of how WebAssembly makes this possible, because it is pretty fascinating. But unfortunately, this talk is so jam-packed with the future, I can't really talk about the things that already exist. And in fact, it's so jam-packed that I can't even go into too much detail on all the things that are in the talk. But if you do want more detail, you can check out the cartoons that I've done about WebAssembly on the Hacks blog, hacks.mozilla.org, and including the post that inspired this talk, WebAssembly's post MVP future. Now, my first articles about WebAssembly came out when WebAssembly was first turned on by default in browsers in 2017, and you may have seen them. This was one of the illustrations from that series. I've noticed since then that a lot of people have a misconception about WebAssembly. They think that the WebAssembly that landed in browsers back then, the MVP in 2017, is the final version of WebAssembly. And I can understand where that misconception comes from, because the WebAssembly community group is really committed to backwards compatibility. So the WebAssembly that you write today will continue working long into the future. But that doesn't mean that it's feature complete. And in fact, that's far from the case. Features are coming to WebAssembly which are going to fundamentally alter what you can do with WebAssembly and with the web. I think of these future features kind of like the skill tree in a video game. So we fully filled in the top few of these features, but there's still this whole skill tree below that we need to fill in to unlock all of the applications. So let's look at what's been filled in already, and then we can see what's yet to come. WebAssembly's story starts with MScript, which made it possible to take these large existing C++ code bases for things like games and desktop applications and run them on the web. And it did this by transpiling that code to JavaScript. But the JavaScript that it automatically generated wasn't very fast. It was much, much slower than if you were to run that code natively. A stroke of insight fixed this, though. One of Firefox's JavaScript engineers figured out that you could do this little optimization in the engine to make this run really fast. And that gave us ASM.js. Once other browser vendors saw how fast ASM.js was running in Firefox, they started adding the same optimizations to their engines too. But that wasn't the end of the story. It was just the beginning of the story. There were still things that engines could do to make this faster. But they couldn't do it in JavaScript itself. Instead, they needed a new language, and one that was designed specifically to be compiled to. And that is WebAssembly. So what skills were needed for the first version of WebAssembly to get this minimum viable product that could run C and C++ code bases on the web? WebAssembly's designers knew that they wanted to support languages other than C and C++ in the future. So they needed a language-agnostic compile target, something like the assembly language that things like desktop applications are compiled to, like x86. But this assembly language wouldn't be for an actual physical machine. It would be for a conceptual machine. That compiler target had to run the code very fast to meet users' expectations for smooth interactions and gameplay. It also needed to load fast, because web users are used to having pretty fast load times. But these kinds of applications are pretty large code bases, and that means that there's a lot to download and compile when the user first goes to a URL. So we needed our compiler target to be compact so that it could go over the internet quickly. These languages also needed to use memory differently from JavaScript. They needed to be able to directly manage their memory. And this is because languages like C and C++ have a low-level feature called pointers. So this is basically where it points directly to a memory address, and it can read and write from that memory address. But you can't just have a program that you downloaded from the internet willy-nilly jumping around in your memory and reading and writing different bytes. So in order to provide a way to access memory like a native program is used to, but keep the browser secure, we had to create something that could give access to a very specific part of memory and nothing else. To do this, WebAssembly uses a linear memory model, and this is implemented with something called typed arrays, which are basically just JavaScript arrays. The only difference is that this array only contains bytes. So when you're accessing it, you're just using array indexes, which you can treat as though they are memory addresses. And this means that you can pretend that this array is C++ memory. So with all of those things in place, you could run desktop applications and games in your browser as if they were running natively on your computer. And that was pretty much the skill set that WebAssembly had when it was first released as an MVP. And it truly was an MVP, a minimum viable product. It allowed certain kinds of applications to work, but there were still whole hosts of other kinds of applications that were yet to be unlocked. So the next achievement to unlock is heavier weight applications. Can you imagine if something like Photoshop were running in the browser? If it were like Gmail, where you could just load it up on any one of your devices and start working on your files? We've already started seeing things like this. For example, the AutoCAD team has made their CAD software available in the browser, and Adobe has made Lightroom available in the browser using WebAssembly. But there are still a few features that we need to make sure that all of these applications, even the heaviest of heavyweight applications, run well in the browser. So first is supporting multi-threading. Modern day computers have multiple cores so that they can process things in parallel, but to make use of those cores, you need support for threading. There's another bit of modern hardware that processes things in parallel, and that's SIMD, which is single instruction, multiple data. So with SIMD, it's possible to take a chunk of memory, a big chunk of memory, split it up across different execution units, which are kind of like cores, and then you have the same bit of code, the same instruction, running across all of these execution units, but each on a different part of the memory. Another hardware capability is 64-bit addressing. Memory addresses are just numbers. So if your memory address is only 32 bits long, you can only have so many memory addresses, about 4 gigabytes. But most modern hardware supports 64-bit addressing, which offers 16 exabytes of memory addresses. And so that's a big difference. Adding 64-bit support will remove the artificial limitation on address space out of WebAssembly. But these applications don't just need to run fast. Load times need to be fast too. One big step here is to do streaming compilation. So that's where you compile the WebAssembly as the file is being downloaded. And WebAssembly was designed for this. In Firefox, we compile it so fast that it's basically done compiling as soon as you finish downloading the file. And other browsers are adding this streaming support too. A tiered compiler also helps. So in Firefox, we have 2 compilers. The first one, the baseline compiler, starts compiling as soon as the file starts downloading. Then another compiler, the optimizing compiler, runs on several threads in the background. And this one takes longer to compile, but it generates code that's extremely fast. And so then, once it's done generating, the optimizing compiler is done generating this code, it will swap out the baseline version, which was good, but not as good for this optimized version. We're also working on a new optimizing compiler. It's called CraneLift, and it's designed to compile code quickly. So this means that it will be faster at compiling code than our current optimizing compiler. And the code it generates is still fast, and we're working to see if we can actually make the code it generates even faster than our current optimizing compiler. But there's an even better trick that we can use to skip compiling most of the time. Unlike JavaScript, if you load the same WebAssembly file twice, it compiles to the exact same machine code. So we can store the compiled code in the HTTP cache. So this means that when a page is loading and it goes to request the file, if that page has already been visited and you already have the same file, you can just return the WASM file, the bytecode, the compiled WASM file, instead of actually having to compile it again. And there are ways to skip even more work. So stay tuned to see what else happens in terms of speeding up load times here. Where are we with supporting these heavyweight applications right now? Well, for threading, we have a proposal that's pretty much done, but the key piece of that, shared array buffers, had to be turned off in browsers earlier last year because of the Spectre bug that was in various chips. They will be turned on again soon, though. SIMD is under active development at the moment. For WASM64, we have a good picture of how this will work, and that's pretty similar to how x86 and ARM got support for 64-bit addressing. And Firefox added streaming compilation last year. Other browsers are also working on this. We also added our baseline compiler, and a few of the other browsers are working on the same kind of architecture. And in Firefox, HTTP caching is very close. And other improvements are in discussion. Even though this is all still in progress, heavyweight applications are already coming to the web today, because WebAssembly already gives these applications the performance that they need. But once these features are all in place, that's going to be another achievement unlocked, and more of these heavyweight applications will come to the browser. But WebAssembly isn't just for desktop applications. It's also meant for regular small module style development that most web developers are used to. If you have a module that does a lot of heavy processing, like a lot of calculation and computation, that's a really good use case for WebAssembly. And again, we're already seeing some of this. So for example, the parser in the source maps library that's used both in Firefox's DevTools and in Webpack was rewritten in WebAssembly, Rust compiled to WebAssembly. And that's now 11 times faster than it was before. And the Gutenberg parser in WordPress is now an average of 86 times faster after having been rewritten to Rust compiled to WebAssembly. So what else do we need? Well, first, calls between JavaScript and WebAssembly need to be fast. When WebAssembly first came out, these calls weren't fast because engines needed to optimize them. This was part of that MVP thing. These calls worked, but they weren't especially fast. We finished our work on this in Firefox over summer, and now some of these calls are actually even faster than non-inlined JavaScript to JavaScript calls. That brings us to another thing, though. You often need to pass data between your JavaScript and WebAssembly functions. So you need to pass in arguments to your WebAssembly and return values from it. And this can be slow, and it can be difficult too. At the moment, WebAssembly only understands numbers. So this means that you can't pass more complex values, things like objects, in as parameters. You need to convert that object into numbers and put it in the linear memory. That's kind of complicated, and it takes some time to actually do that conversion. So we need this to be easier and faster. We also need to integrate with ES modules. Right now, you can't use the import and export keywords with WebAssembly modules, but that means that the WebAssembly module isn't going to be part of your JS module graph. Just being able to import and export doesn't get us all the way there, though. We also need ways to distribute and bundle WebAssembly modules. What's the NPM for WebAssembly? Well, what about NPM? What's the Webpack or parcel for WebAssembly? Well, what about Webpack and parcel? These modules shouldn't look any different to the people who are using them. So why should we create a whole separate ecosystem for them? And there's one more thing. Support for older versions of browsers, even those that don't know what WebAssembly is, like IE11. So where are we on all of this? Well, calls between JavaScript and WebAssembly are fast in Firefox now, and the other browsers have prioritized this recently. For easy and fast data exchange, there are a few proposals that will help with this. The reference types proposal makes it possible to use references as arguments and as return values, and this references to an object from outside of WebAssembly, so a JavaScript object, or for other things outside of the browser, it might be a different kind of object. Another proposal, the host bindings proposal, will make this even faster. Another thing we can do to make things easier, to make it easier to deal with memory, is to make it so that when you have these data dependencies between JavaScript and WebAssembly, that the JavaScript code tells WebAssembly exactly when it can clean out parts of linear memory. Because when JavaScript's done, when you share something from WebAssembly and JavaScript's done with it, currently, right now, you actually manually have to call free on the linear memory. But we can make that automatic with something called weak refs. So these proposals are all in flight. And in the meantime, the Rust ecosystem has created tools that handle all of this for Rust code. For ES module integration, the proposal is pretty far along. For toolchain support, there are tools like WASMPack in the Rust ecosystem, which automatically runs everything that you need to package your code for NPM. And the bundlers are actively working on support. Finally, for backwards compatibility, there's the WASM2.js tool. And that takes a WASM file and spits out the equivalent JavaScript. Now, this JavaScript isn't going to be fast, but at least it will work in older versions of browsers that don't know about WebAssembly. Once we unlock this achievement, we unlock the path to another two as well. So one of these is rewriting large parts of JavaScript frameworks in WebAssembly and making it possible for statically typed compiled to JS languages to compile to WebAssembly instead. So this is languages like Scala.js or Reason or Elm. For both of these use cases, WebAssembly needs support for some high-level language features. So first, let's look at rewriting parts of JavaScript frameworks. For a framework like React, you could parallelize the DOM diffing algorithm, that virtual DOM algorithm. And you could do it with something like Rust that has very ergonomic support for parallelization. So that would make it a lot easier to write this algorithm in parallel. And you could also speed things up by reducing memory usage and allocating that memory differently. But you would still need to interact with JavaScript objects, things like components that the user has written, from that code. You can't just write everything in linear memory, because that would be difficult and inefficient. So you need to be able to integrate with the browser's garbage collection at the same time. Now, some of the JavaScript objects are going to need to point into linear memory, and sometimes the data in linear memory will need to point back out to JavaScript objects. And if this ends up creating cycles, it can mean trouble for the garbage collector. It doesn't know when to collect the garbage. So WebAssembly needs integration with the GC to make sure that these kinds of cross-language data dependencies actually work. And this will also help those languages that I talked about that compile to JavaScript, like Scala.js, Reason, and Elm, because these languages already use JavaScript's garbage collector when they compile to JavaScript. And that's the same garbage collector that WebAssembly will be running when it's being used in the browser. So that means these languages don't need to change their GC. We also need better support for handling exceptions. Most WebAssembly modules currently don't support exception handling. But JavaScript does have exceptions, so even if you've compiled your code to work without exceptions, JS may throw one into the works. And if your WebAssembly calls a function, a JavaScript function, that then throws, it's likely that your WebAssembly module won't know how to handle that exception. So we need to make that work better. We also need good debugging support. Dev tools today make it really easy to step through your JavaScript code. We need that same thing for WebAssembly. And finally, for many functional languages, you need to have a support for something called tail calls. So where are we on all of this? For garbage collection, there are two proposals currently underway. There's the typed objects proposal in JavaScript and the GC proposal for WebAssembly. And our team already has a prototype of these working. However, it's still going to take some time to go through standardization, so we're probably looking at sometime next year for this. Exception handling is still in the research and development phase. For debugging, there's currently some support in browsers, but it's still not ideal. So there's a subgroup of the WebAssembly CG that's working on specifying that. And the tail calls proposal is also underway. Once those are all in place, we'll have unlocked JS frameworks and many compiled to JS languages. So those are all of the achievements that we can unlock inside of the browser. But what about outside of the browser? Now you may be confused when I talk about outside of the browser, because isn't the browser what you use to view the web? And isn't it right in the name, WebAssembly? But the truth is technologies like HTML and CSS and JavaScript are only part of what makes the web. They're the visible part, so they're the most obvious part. They're what you use to build user interfaces. But there's another really important part of the web which has properties which aren't as visible. That's the link. The link's innovation is that I can link to your page without having to put it in a central registry or ask you or even know who you are. It's this ease of linking that made it possible for us to form these global communities with people that we don't know. But there are two problems here that we haven't addressed just by having this link. So the first one is you go visit the site and it delivers some code to you. How does it know what kind of code it should be delivering to you? Because if you're running on a Mac, then you need different machine code than when you're running on Windows. Does a website need a different version of the code for every possible device? No. Instead, the site has one version of the code, the source code, and that's what gets delivered to the user. And then on the user's device, it's translated into machine code for that device. The name for this concept is portability. With it, websites don't need to know what kind of device you're running. But that brings us to a second problem. If you don't know these people whose web pages you're going to, how do you know what kind of code they're giving you? It could be trying to take over your system. Doesn't this vision of the web, running code from anybody whose link you follow, mean that you have to blindly trust everyone who's on the web? This is where the other key concept from the web comes in, and that's the security model. And so this is the sandbox. Basically, the browser takes the code and puts it inside of a sandbox. It puts a couple of toys in the sandbox too, so that the code can do some interesting things, but it leaves dangerous things outside of the sandbox. So the utility of the link is based on these two things. Portability, being able to deliver the same code to any device and have it run, and the sandbox, the security model that lets you run code without putting your machine at risk. So what difference does it make if you think about the web in this way? It changes how you think about WebAssembly. You can think of WebAssembly as just another tool in the browser's toolbox, which it is, but it's not just that. WebAssembly also gives us a way to take these other two capabilities of the web, the portability and the security model, and bring them to other cases that use them too, that need them too. We can expand the web past the boundaries of the browser. Now you may be thinking, this already happened with Node.js. But as it is today, Node doesn't quite get us there. It doesn't give us full portability, and it doesn't give us the same security, the same confidence to run untrusted code either. With Node, it's possible to run JavaScript on servers and other devices that don't have a browser. So that does give us some portability. But you still need native modules in a lot of cases, either because the native code performs better and you have a performance-sensitive task, or you already have code written in a language like C or C++, and you want to reuse it in your app. But native modules aren't portable. They have to be compiled specifically for the user's device ahead of time. We're also still missing security. Node could have taken the sandbox from the browser, but Node made the design decision early on that JavaScript modules would have full access to system APIs. So JS modules can do things like read and write files on your machine. These capabilities, things like full direct file access, are the dangerous toys that aren't available in the browser's sandbox. Even though these toys are dangerous, for the kinds of use cases that Node was built for, this kind of access does make a certain kind of sense. The thing I want to make clear here, though, is that Node had a choice. They made a choice, and it's that they had a choice to make with JavaScript. For JS modules, they could have decided to go with a sandbox-style approach. And so that was the choice they made, not to use a sandbox for JS modules. But for native modules, Node actually had less of a choice, because it's hard to sandbox native code. Now for Node, this is a moot point. This design decision has already been made. So if you're running a Node application, you're basically saying, I trust this code. But what about other use cases? Wouldn't it be nice to have both the portability and the security of the web? WebAssembly does make this possible. WebAssembly starts with the advantages of JavaScript, the portability and the ability to be sandboxed. What it adds is performance, which means that developers don't have to resort to unsandboxed native code in order to get that performance. So that means that we can bring this security and portability to use cases outside of the browser, use cases for things like the blockchain or the cloud or the Internet of Things. And I'll talk more about how it does this in a second. But first I want to finish up on Node, because even though Node has no use for WebAssembly's ability to run untrusted code, WebAssembly can still help Node. So how could we improve Node using WebAssembly? We could bring full portability to Node. We could eliminate the need for native modules, ones that are compiled on the user's device for that specific kind of device. These could be written in WebAssembly instead and just compiled once. And these modules could run across all devices, just as JS modules do now. The only problem here is that WebAssembly doesn't have direct access to the system's resources. So we need to pass in functions that can work with the operating system. Now for Node, this would probably be a lot of the functionality that's in things like the C standard library, or things that are part of POSIX, the Portable Operating System Interface, which is an older standard which helps with compatibility for Unix-like OSs. To make that happen, the Node core folks would need to figure out the API that they need for their different use cases. But wouldn't it be nice if that was actually something standard? Not something that was constrained just to Node, but could be used across other runtimes and use cases too? A POSIX for WebAssembly, if you will. A PWASIX, a Portable WebAssembly System Interface. And if that were done in the right way, you could even implement the same APIs in a slightly different way for the browser. Now these functions wouldn't be necessarily part of the WebAssembly spec itself, and there would definitely be certain hosts that didn't make them available. But for those platforms that could make use of them, there would be a unified API for calling these functions, no matter which platform the code is running on. And that would make universal modules, ones that run in both the browser and in Node, so much easier to write. So, is this something that could actually happen?
Well, we and others are working on it, and I think we have a pretty good chance. I will talk a bit about some of the more recent developments in this space, but before I do, I want to say some more words on some of the use cases. One of them is the domain of CDNs, of serverless and edge computing. CDNs more and more want to run code instead of just serving static resources, something that only servers used to do. But a CDN works at a different scale, where a traditional server might process hundreds, perhaps thousands of requests per second. A single machine in a CDN easily has to scale to tens of thousands, perhaps even more requests per second. WebAssembly allows the Fastly CDN, which serves a significant fraction of the internet's traffic, to run untrusted user code at the scale they need for their CDN. To get there, they use WebAssembly in some really fascinating ways. We unfortunately don't have the time here to go into the details of how they get to that scale, but their CTO, Tyler McMullen, gave a talk back in September titled Software Fault Isolation and Edge Computing, and you should watch that talk. The point for today is that WebAssembly doesn't only give them the scale needed, but also the speed for every single request and the safety for running this untrusted code. Now, if this were a browser environment, this would all be done through JavaScript. And what's really the basic requirement here is their customer code needs to be able to talk essentially to the outside world, to be able to process these network requests and send back replies. And in a browser, JavaScript provides the means to talk to the outside world, because you always use WebAssembly through JavaScript that loads the WebAssembly module and provides it with the environment it runs in and the ways to talk to the outside world. At Fastly, they are not using WebAssembly together with JS. They are using only WebAssembly in their own environment, so they needed something else. They needed their own runtime and their own runtime environment. And runtime in this case means taking a WebAssembly compiler, something that takes the WebAssembly bytecode and turns it into machine-specific code for the machine that it actually runs on. And then adding functions that can be used to talk to the outside world and do fundamental things such as memory management. Functionality like this is commonly called a standard library, as Lynn described earlier. Now at Fastly, for the WebAssembly compiler, they chose the one we are working on at Mozilla, called Grainlift, which Lynn also mentioned. And Grainlift is pretty small and self-contained, so you don't get large code bases as dependencies imported into your project. And we are also integrating it into Firefox, so we are making sure that it is both safe and fast. Now for the runtime environment, they had to create their own, essentially from scratch, because there is no standard for that. And creating that means looking at how do we need this code to talk to the outside world exactly? How do we provide this? What are the functions we provide? How do we provide them? How do we expose them to JavaScript, to WebAssembly code? This is possible today, but it is a lot of work. It's hard work, and it takes a lot of resources. Nevertheless, there are a number of projects in flight in this space. One of them is Fastly's. Another is the WAVM VM built on top of the LLVM compiler toolchain, which is also used by the most successful C++ and C compilers and the Rust compiler. Another one is WASMJIT. And we are also building one at Mozilla based on Grainlift. And it's called WASMTime. And if you're interested in hearing more about that and the use cases we envision for it, then come find me after this talk. So with a runtime like this in place, we can cover the CDN use case as described, but also a number of other use cases. And I'll briefly mention a few of these. People are working on building blockchain platforms with WebAssembly, where you can write smart contracts in all languages that can compile to WebAssembly. There's interest in the IoT space for abstracting away the device specifics and being able to make use of the portability. And people are writing portable CLI tools with WebAssembly. We've also seen interest from companies building game engines, where WebAssembly can be used as essentially a scripting sandbox for untrusted game logic, perhaps even bots that other parties can provide to run in your game environment. And finally, with projects like WASMJIT and Nebulit, some folks try to make WebAssembly work inside operating system kernels. And this is sort of an interesting use case because it's a domain where WebAssembly can outperform native code, because you would never run native code inside an operating system kernel. It's way too unsafe. But with WebAssembly, this becomes feasible, and there are use cases where you have to call into the kernel a lot. And if you're running outside the kernel, that means a lot of overhead. And this code running inside the kernel can be massively faster for these use cases. We talk more about these very different environments in this blog post Lynn mentioned earlier about the post-MVP future for WebAssembly on hacks.mozilla.org. We published that back in October. For today, one of WebAssembly's big selling points is worth some more description, and that is the portability that Lynn mentioned. And that sort of goes both ways. It's about being able to run the same code in different environments on different CPU architectures, but it also means providing the same interface for functionality that is common to all these different use cases. For JavaScript, this kind of portability is in large part provided by, well, the language itself. JavaScript doesn't have a huge standard library, but it has enough of one that you can write fairly large modules for applications with just relying on things that are part of the JavaScript language itself, not this runtime environment. And so you can run that code in the browser and in Node just the same. And then there's another sort of interesting type of portability for JavaScript, and that is relevant to code running outside the browser, exclusively outside the browser. And that is provided by sheer dominance of one runtime, of Node. Because really, if you're running code outside the browser in JavaScript, chances are you are going to run Node and not another runtime. So even though there is no standard for a runtime environment that goes beyond what the language provides outside the browser, you can rely on a set of APIs being available because Node makes them available. If we had the standardized runtime environment for WebAssembly, we could get to a fairly similar situation, but in a better way. We could get to it in a way that allows you to write code expecting a set of rich APIs to be available, no matter what the runtime is. And we don't have to rely on a one-size-fits-all, because a one-size-fits-all, yes, it might fit, but it doesn't fit anybody really that well. And there's a broad space of these different use cases, and there's space for a number of different runtimes. And you shouldn't need to know which of these you target for every single line of code you write. You should be able to just say, apart from very specific parts of my application, the core, I'll just write WebAssembly, and it'll work in all these different runtimes. For the standard library, we could say, we'll just use POSIX and be done with it. It's established as a standard, it works, it makes porting to the platform easy. So what's not to like about that? And in fact, runtimes like WAVM do something very close to that. Unfortunately, it eliminates one of WebAssembly's core advantages, the security model, and in particular, the sandboxing. Lynn talked about how Node had a choice to make, a choice between keeping that sandbox that JavaScript runs in the browser, or giving it an easy way to talk to the outside world. And now we have the same choice to make, essentially, but for WebAssembly this time, not for JavaScript. Do we go with this easiest route, but give up on sandboxing, or do we do something different? Something that allows better control and leads to better security and auditability. And the last point, I think, is really important. Before running an application, you should be able to see what is the worst thing that this application could do to my system. And not by reading the code in detail, but by just looking at the outside, sort of looking at the label. Can it steal my Bitcoin wallet? Maybe not run that code. Can it just operate in its directory where you wanted to process some file and then give the result back in that same directory? That's probably fine. And this is something, this auditability and really proper sandboxing, that is almost impossible with POSIX. And to the degree that you can approximate it, you need things that operating systems provide. And they provide it in very different ways between different operating systems. So even if you go to all the lengths needed for that, there goes your portability, or at least a significant part of it. And even though, if nothing had changed since Node was created, we might actually end up making the same choice as Node did. Because what they did made sense. Lynn described how there really wasn't a different way to give their code a way to talk to the outside world. And this is because API designs for how to do the security and auditability and proper sandboxing while still making the system usable enough. Those existed, but they existed in academia, and they hadn't been tested in the real outside world at scale. Luckily for us, this has changed. Better designs exist nowadays, and they are being tested at scale. For example, Google are building this whole operating system called Fuchsia around just such a design. And for Wasmtime, we are working on a standard library around such a design that'll make it easy to build secure, auditable, and portable applications and modules that'll work for all of these different use cases. So with this standardized API, you could get the same flexibility that you have with Node, but still have security and auditability. And you can run the same code not only in a single unspecified runtime, but in a variety of runtimes fit for different use cases, such as Wasmtime, Node, and the browser. With all this, it is still important that you have the same ease of use in your development, because if it's too hard to develop for, there won't be any uptake, and we lose all these advantages. In particular, that means you should be able to use your normal tool chain to target this environment. We're initially focusing on really seamless support for Rust that brings the Rust ecosystem to this platform in all its richness. Rust has this package manager called Cargo, which is sort of similar to NPM, and has a lot of packages that are similar to NPM packages that provide a lot of reusable functionality. We're bringing all of that to this platform. We actually also have code running already for C and C++, and other languages will be supported eventually too. Lynn also mentioned that browser vendors are working on proper DevTools support for WebAssembly. And this is the other important part of a workflow that needs to be really well supported. And for outside the browser use cases, we believe that DevTools are just as important. And outside the browser, that mainly means debuggers. And you should be able to use the debuggers that you are used to. And so for Grainlift and Wasmtime, we are working on support for using debuggers such as LLDB and GDB, and perhaps even more importantly, the IDEs that use them under the hood, such as Xcode and Visual Studio Code. Without any changes to any of these tools, you should just be able to make use of them. So as you can see, there's a lot of active development in this space, and we are all working hard to make it easy to target this environment and without jumping through too many hoops and to properly debug your code.
Now let's zoom back out and look at this skill tree. I said at the beginning of this talk that people have a misconception about WebAssembly. This idea that the WebAssembly that landed in the MVP was the final version of WebAssembly. And I think you can see now why this is a misconception. Yes, the MVP opened up a lot of opportunities. It made it possible to bring a lot of desktop applications to the web. But we still have many use cases to unlock. From heavyweight desktop applications to small modules to JavaScript frameworks to all of those things outside of the browser. Nodes, serverless, the blockchain, the Internet of Things. So the WebAssembly that we have today is not the end of the story, because WebAssembly still has promise to keep and many places to go before it sleeps. Now before I finish up, I just want to give a little bit of thanks. I enjoy working at Mozilla because I get to work on cool stuff like WebAssembly, but I also enjoy it because I get to work with some of the smartest and kindest and most engaging colleagues I've ever had a chance to. And I had a chance to collaborate with 2 of them on this. So, of course, Till Schneidwright is one of them. And the other is Luke Wagner. He was one of the co-creators of ASM.js and was also a major driving force in making WebAssembly happen. So thank you to both of them, and thank you all for listening.